Okay, it is a great honor to say welcome to the keynote speaker of this conference, Matti Tedre. Matti lives in Joensuu, Finland. I think he'll pronounce it himself later on. University of Eastern. He is a professor of University of Eastern Finland. He holds a PhD in computer science, and he is also an associate professor at the Stockholm University in Sweden. Matti wrote several very interesting articles and books. The latest one is just called Computational Thinking. He wrote it together with Peter Jennings, another, Peter Jennings is a grand old man in this field, almost as old as Peter Nauer. Matti isn't that old, even though the pictures on his website tells us that he has been younger. Matti is, besides being a very inspiring writer on things on computational thinking, he's also a very accomplished, extreme ironing man. So he irons stuff. Go to his website and look at it. It's very interesting. You could also go to YouTube and learn everything there is to know about computer science in just 3 minutes. I think you made a video for your students. So type in his name and computer science, and you'll see a very interesting video on computer science. But today you'll just enlighten us on computational thinking and also the history and all the good things and bad things we are doing today in this area. Welcome, Matti.
This is good.
Okay.
Right, thanks. It's really an honor to be here, and I'm really happy that I got invited. My name is Matti Tedre, and I come from University of Eastern Finland. I'm right now at a visiting professor at Technical University in Technical University of Vienna in Austria. So I was asked to talk a little bit about CT, computational thinking, and in the family we just call it CT. So give an overview of what it is about, and I was told that there are a lot of people here from different areas, from different fields, and from different kind of strands of society. So I try to make it not too technical and try to make it not too basic, and trying to balance there. So so if you are at any of the extremes, then then just my apologies. So this talk is based on a recent book called Computational Thinking, and a bit earlier book called The Science of Computing. And I thought that it's always a good idea to first say what you're going to say. So this talk it's divided into 4 themes. First, I'll talk about why, then I'll talk about what, then I'll talk about how, and then I'll talk about so what. So let's see what comes out of it. So I'll talk a little bit about the intellectual backdrop of CT, and then I'll go into so why are we talking about it? What are people doing about it, and what are the challenges? Right. So I think that the first reason why we really are talking about CT and why it's such a big deal is that there is no science pretty much today without computing. So what happened is that almost every laboratory has one single instrument that is common to them, and that is the computer. So we use computers, to crunch our data from experiments, and we use computers to crunch theories and do all kinds of stuff that we could do without computers, but we are now able to do really at massive scale with computers. But we have also then got new scientific methods that allow us to do things we could never do before. So we can now experiment on galaxy formation and collision of galaxies that wasn't possible before. We can now experiment on elementary particles that we don't even know if they exist, but we can experiment on them. We can experiment on national economies and things that was never possible before. And that has made a lot of people say that the twin pillars of science, theory and experiment, are now joined with a third pillar that is computing. And that has also led us to kind of reconsider the limits of science, because the more science depends on computing, the more the limits of science are the limits of computing. And that is a whole new epistemological boundary for us. We can't know through computing something that we can't compute. So that really draws a lot of new boundaries for what we can know. And it's also interestingly led to a new epistemology, a new idea of what do we consider to be right, wrong, correct, provable, and so forth. And models or computer simulations are not even the kind of a thing that can be right or wrong. They can be better or worse. They can emphasize some things and then ignore others. And models are just very different from theories that we used to rely on. Take, for instance, global warming models. I'm pretty sure that there are about 200 different models for global warming. Most of them point to one direction or the other with variations, the direction that things are warming up. And then others say that no, they are not. And it's very hard to distinguish between all these models and say which one of them is right, because none of them is right. No model is right. Models just are not the kind of thing that can be right. So which has led us to really reconsider what do we say when we say we need to prove something, because prove is a really strong word, and we need to avoid those kinds of words with models. And then, in addition to these fundamental changes to how science is done, we also have new ways of collaborating. And nowadays, it's not at all unusual to have 500 people using the same data set to study the same things. Here's the Large Hadron Collider, and it's not an exaggeration to say that sometimes there are 1,000 people studying the same data sets. And now I have seen articles with more than 500 people involved in the list of authors. So the list of authors is 25, 30 pages, and then comes the article 6 pages. Science is also, computing has also made it possible for us to do open access, open data, and open peer reviews. But I think that the most important and the most fundamental change in science that has happened is that in many ways we have had to look very closely into what are we really studying. Because in many sciences we have now started to see our subject of study in a very different light in terms of information flows. I think biology is one of the best examples of this. So biology started to change already in the 1950s or 60s, but in the 1980s there was a massive shift into bioinformatics. Here David Baltimore won the Nobel Prize in 1975 for his work on interactions between cells and viruses, where he threw away the old idea of biology as study of life, living matter and so forth, and replaced it with an idea of studying information flows. So he studied biological phenomena thoroughly and purely as information flows, thus turning biology into an information science. And today we have no problem talking in information terms about biology. We talk about our genetic code. We talk about our genetic information being stored in our genes. We talk about making babies in terms of, I guess transferring our genetic information or copying our genetic material. So we really talk also in our just everyday talk, we talk in code information terms about many biological events and things. And today, physics has also done a bit of similar shifts. Here, Ken Wilson won the Nobel Prize in 1982 for renormalization group, essentially studying physics as information processes. Humanities have followed the suit. We have seen massive studies on authorship, for instance, massive studies on history that rely on computing. We have seen all kinds of studies of emotion, communication, and so forth that are completely fundamentally information-based. And learning analytics does the same for educational sciences and so forth. So there has been this massive shift in all areas of science, in so many areas of science that science just is not the same as it was before. The second massive shift why we are really talking about these aspects is digitalization of society. And that just refers to digitalization of everything, including money, property, bureaucracy, and all this stuff. It also relies on intuitive interfaces. Programming was the main interface for controlling the computer in the 1950s, 60s, 70s, and so forth. Then we got better and better interfaces, and programming started to lose currency. Today, we can do amazing things with technology without actually doing any programming. We can do. I think that we can safely say that the role of programming in controlling the computer has been dramatically dropping, because we have got interfaces that allow us to do really great things without doing any programming. Sensor technology has come to play, and you can buy from Alibaba, like 1,000 sensors for $100. So sensors have become really cheap, and you can put them anywhere, which has led to data deluge, to a explosion in the amount of data that we now collect. And nowadays, computers have more and more data about the stuff around them, and computers can sense so many things that in many ways computers can see and sense more than we do. And finally, then we have also made them connect together. This is where it probably kind of started, and then it evolved eventually into a ubiquitous world of computing, where interfaces are invisible and where intelligence is ambient. And that now has allowed us to transform first routine jobs. And this has been something that keeps those government people and policymakers really on their toes, because a really important elements of work life are disappearing as we speak. Routine jobs are those jobs that are people's first jobs. Jobs that you can do with no education, jobs that you can do with no work experience, jobs that are low paying but are really important gateway into work life and into integration in society. And those are being transformed at the fast pace. A lot of my friends had their first job working in retail, which is now replaced by all kinds of automation. This is Amazon Go, where you just walk in and you walk out and you are billed automatically, and there are all these kinds of alternatives where retail jobs are just disappearing. Fast food or flipping burgers used to be another really common job, first job for many people, and that is disappearing through automation. There are more and more sophisticated machinery that can do the whole thing, from ordering to making to delivering your food. Rental services, movie rentals and so forth used to be a really common routine jobs, as was banking, hotel clerks and so forth, all automated now, and warehousing. So we are losing at the fast pace a lot of jobs that are routine, but which serve a really important place in the society. But it didn't stop there. We have seen at the same time a massive transformation also of knowledge work. And this is where we people felt that we are safe. We always felt that, yeah, a computer can do all those physical routine jobs, but it cannot do what I do, because what I do involves intuition, it involves understanding what's going on and so forth. But we have seen that more and more jobs that we thought are secure from automation are actually being automated at a rapid pace, and those are knowledge work jobs. Medical diagnosis is one. I would like my lung disease being diagnosed by a computer much rather than a doctor, because computers are just so much better at it. Accounting, things that used to be made by people, is nowadays more and more computational. Even design jobs, which used to be kind of the human job, are more and more turning into computer-based ones. Computers are able, using evolutionary techniques, make these designs that are stronger and lighter than any human-made designs. They imitate evolution in a way that they test millions of combinations and then simulate them for which ones are stronger and which ones are not. Customer service jobs we have seen have turned into bots. Just today I talked with UPS bot, the parcel delivery bot, explaining that I'm not in Finland, please deliver it later. And I don't think that a human ever read that discussion, but I just told him, I'm here, and I guess it was a bot. It was Larry. Journalism in many US newspapers has turned into robot journalism, as they call it, which is a horrible name, but but I didn't choose it. A lot of newspapers use computers to write their sports news, because I guess those are not the ones that win journalism prizes like Pulitzer prizes, but still, they deliver you the information that you need. Company annual reports are being more and more written by computers. McKinsey, for instance, I think is just doing one of those. And transportation, as we know, has been made into more and more automated ones. I guess that at the point where auto industry has invested $45 billion into self-driving cars, I think we can pretty safely say we are going to have them on the roads. I don't think that they are going to spend that much money for something that won't happen or that might happen. So I think we are pretty sure about it. So what we have here is we have new means of knowledge production. We have new epistemology of science. We have rapid digitalization of societal structures and processes and new ways of automating knowledge work. And now the question is, so how do we prepare people for a world that looks like this? What do we need to do in education that prepares children and adult learners to this kind of a world? And that, of course, you know, is the topic of what we are talking about here. And a computer scientist's solution to that is always computational thinking, because a computer scientist, of course, sees everything as, oh, computational thinking. If it's all computational, then why not teach it? Right. So that was pretty much the sort of why. Then we come to what. There must be a million definitions of computational thinking, and not only the ones shown in the past 12, 15 years, but spanning like 70 years back, and even more. Just the ICILS report, is that how you pronounce it? Yeah, well, just the report that you got today quoted at least half a dozen or more of these definitions of computational thinking. And there are so many ways of talking about it. But I guess that on a very high level, they share some things common, which are ability to see the world as information flows, in terms of information, I guess, which is the ability to model things, and skills to make computers do jobs for us. I think automation is the other key issue there. And then ability to design for people and with people. I think those are sort of some things that are quite much agreed upon. There are a lot of different views on that. Right. So the same thing has been called by many names. It used to be algorithmizing in the 1950s, algorithmic thinking in the 70s, procedural thinking, procedural literacy, computational literacy, and in the 1980s it was called computational thinking already. And there are a bunch of other words used for roughly the same thing, not always quite the same, but at least describing the same kinds of efforts that we are now taking, describing the efforts that try to solve the same kind of issues that we are trying to solve here. Well then, how do we teach kids this, children and adults, these computational thinking ideas? I think that it's really important that we don't limit ourselves to just K-9 education or just schools, but it's also adult education, continuing education and so on that we really need to consider here. Some of the really common things that have been said about computational thinking include these really high-level things like logic, algorithms and decomposition, like patterns, abstraction and evaluation, which are kind of a very high-level ideas which don't tell almost anything about the actual things underneath. Then you have things like tinkering, creating, debugging, persevering and collaborating and so forth, which I would say if you would talk to a mathematician or physician or physicist or I mean chemist or anybody in the field, they could say that actually a lot of those are actually our field things too. So computational thinking is a sort of umbrella term for a bunch of ideas that we have borrowed from many different fields. My colleague Arnold Pierce has called computational thinking fake news because he says that actually every one of those things can be named in some other fields too. So there are very few things that are actually unique to computing that can't be found anywhere. But I think that we can still warrant to call it computational thinking because we are working on a very unique thing, the computer, the digital computer, programmable computer, that is very different from any other technology that we have had before. What computational thinking got? after it was sort of, it became a hot thing again. I think, I don't know which wave was it the fourth or fifth wave now in early 2000s. It started to get really a lot of funding. NSF gave hundreds of millions of dollars to computational thinking. Obama administration gave $4 billion to teaching teachers. It started to get journal special issues. You started to see more and more research centers on computational thinking. You started to see massive organizations coming up with their own curricular elements for computational thinking. And it started to trend in about 2007, 2008, and more people started to take notice. And now it's I would say, a mainstream thing in computing education to talk about computational thinking. Although now you see a lot of people also questioning the value of computational thinking in comparison to classic computing education, classic programming education, classic computer literacy, and so forth. So there are a lot of people who are asking, so what's the new thing here? What is here that we haven't seen already in the past 40 years? So that I think is a very relevant question. Right. So now, how are people teaching computational thinking? What are the kind of ways of teaching it? What are the routes to trying to convey these ideas that drive our society? And we have seen a massive range of initiatives, and not all of them, I think, belong under computational thinking per se, but are just computing education, generic computing education initiatives. You see things like modeling and experimenting on computers. You see creating visual programs on computers. This is my favorite. This is my first programming language, which was Logo. I was 8 years old. It was a great language. We can see using computing in other subjects. We can see experiments on building and controlling machinery. These are all really computing specific. We can see these, games, puzzle games being introduced in computational thinking, playing games without a computer, really innovative ways of teaching CT without using computers. We have seen these visual programming tools. We have seen attempts to design systems for humans, creating and making these e-textiles. We have been doing, in my group, we have been doing these machine learning systems for kids, preschool, primary school, secondary schools, and so forth. And we've been teaching also image recognition, so some of these are from our group. But then, more and more, I think, we are facing also challenges to what we consider computational thinking. And a lot of these challenges are the same challenges that computing education has faced for the past 40, 50 years. The first challenge, I think, is that coding is really low ambition there. Because when we talk about the computer revolution, we just talk about these massive shifts in society, in science, in organization, in our thinking. And now our solution is to teach coding. And I think that just doesn't ring the right bells to me. It just doesn't sound to me like epistemological revolution that computers were supposed to trigger. It doesn't sound to me like the pedagogical revolution that Papert wrote about. It just doesn't sound to me like the scientific revolution that we are talking about here, to be able to do some basic coding. The second challenge is we really cannot afford to be dogmatic about it. We need to be pluralistic and involve other fields to this, and not only computing. Because if there is one thing we see from history, it is that if we just design these computational thinking initiatives between computer scientists, they are bound to fail. I'm sorry, this is bad news for some of us, but like me. But we need to reach wider. The third challenge is we don't even know which way does programming play in this picture, because nowadays a trend is to say that when you learn computational thinking, you learn programming skill. But there is no evidence on that. There is not at all evidence on that. There is evidence on programming practice leading to computational thinking, and the evidence is me and probably most of you who program, because we have learned our computational thinking through programming. So there is a lot of evidence on this. There probably is much less evidence on this. We don't know if this works. Right, and we need to find evidence. And that leads to challenge 4. Whatever we do in CT, we need to build an evidence base. We need to really test our claims about CT before actually overselling it, because overselling this idea is the surest way of making sure that it's going to be rejected at some point as something that didn't deliver. Next challenge is, okay, what do we need to teach? How do we need to teach? And at what age do we need to teach? That's a pedagogical question, and there are still a lot of open questions about pedagogy. Those who work with computational thinking are really asking questions about how do we teach things? And the problem, I guess, starts from even our problems in resolving what to test and how. This is a bit bad place to be talking about this when this ICILS conference, which it actually says that we have tested it. But I would say there is no consensus on whether you need to test competencies, knowledge of concepts, communication of ideas, design skills, or what. So and this problem of what to test and how, of course, goes back to the question of what is computational thinking. So different answers to what is computational thinking lead to different ideas on how to teach it and how to test it, of course. Then I think that I saw in Danish, I don't know Danish, but I think that one of the questions was what are the problems what are the historical problems that we are going to repeat? Was it? I'm not sure. But I think that if there is one historical problem that we shouldn't repeat is, let's train the teachers, because if there has been an issue of why computers are not taught in schools more, it's because of lack of teacher education. And we really need to find out how to train the teachers to do it. We need to be renewing with the field. Right now, we are looking, when we are teaching computational thinking to children, we are looking at K to 9, so they are going to be adults in 10 years, they're going to be in working life in 15 years, 20 years. We can't be teaching stuff that was relevant 15 years ago, which is often what we are actually doing in computational thinking. I'm dead serious. When we are talking about programming concepts, basic programming concepts, maybe that is not the right way to go. I'm a bit skeptical about the role of coding in the curriculum. I know that that this gets a lot of hate, but that's my feeling, because we have seen automation of coding in so many ways happening. Development environments have relieved coders of so many things that they used to be doing manually before. I was on the stage with Microsoft representative like half a year ago, and she said. All right, yeah. She said that that Microsoft in Finland hasn't hired a coder in 2 years, because that's not what they are looking for. They are looking for data scientists. They are looking for machine learning experts who are not doing coding. They are actually doing a very different kind of stuff. They are looking for people who can curate data, who can clean up data, and then do all kinds of magic with data streams. Microsoft actually has now a thing called Deep Coder. You should go and see it. The reason why Microsoft bought GitHub is that they can use GitHub's code to teach their deep learning algorithms to write code. It's really amazing. Go and see it. Right. So these were some of the challenges that we face with computational thinking. And these are some of the challenges that really bother a lot of people because of the changes in society, because of the changes in all those kinds of things. But then I think that there is an undercurrent of other issues that are really worrying a lot of people. At least they are worrying me a lot. And I think that we need to be also talking about what kinds of computing education do we need to answer those issues. And those issues are, for instance, we have tools to collect massive amounts of data about users from all kinds of visible and invisible things they do. I mean, I guess that it's not really exaggeration to say that we are able to track people so that we exactly know what you did last summer. But that's not the gist. We are also able to track you and model you so that we know what you're going to do next summer. Because when we have massive numbers of amount of data about people, we can very accurately predict what a person like you, a person with your profile, will do in a situation where you are going to be. And learning coding, I'm not sure if it's the right thing to do here. Then we know that profiling reveals also what you try to keep secret. So we know what websites you surfed last night. We know where you were 2 o'clock in the night. We can even infer things that you haven't done, but you would like to do. So whatever you think is secret, massive amounts of data ensure that there are no secrets. And then we are doing emotion farming, which knows how to make you happy, sad, or angry, because this is a part of how social media business works. Social media business is based on knowing what makes you happy, based on knowing what makes you sad and angry, and so forth. And these are the things that really worry us. Attention engineering is a way of looking into using the things that they learned about your behavior that can keep you addicted. And behavior engineering is focused on making you do something, like swaying elections, make you vote for Brexit, make you vote for Trump, make you vote for whomever you don't like. And authorship identification makes sure that there is no anonymity. When there is enough data, there are no secrets, and it doesn't help you that you serve on private mode. It really doesn't. So, and the things that worry me about the most is that, right, we as adults may have given consent to this data collection, but right now, by the time kids turn 13 years old, there are 70 million data points about them already stored. So we are raising a generation of people of whom we know everything from day zero. So now my question is, what kind of computing education helps to tackle these? And I think that this may not be completely relevant to computational thinking, but I think that it's relevant in the broader theme of computing education. Thanks. That was my bit.